Hello everyone, my name is Aaron Kent, and this is my Physics Lab 1 demonstrating constant velocity. Now, just for a little bit of intro to lab, this lab takes into account Newton's second law, specifically, so we're going to be focusing on the net external force. Now, the purpose of this lab is to show the momentum principle, specifically that if there is no acceleration, means of speeding up and slowing down, then the overall speed as the ball rolls will stay the same. So essentially, as we all know, the momentum principle is P, which is used for momentum, I don't really know why, is equal to m times v. What this purpose of the lab is trying to show is if acceleration equals 0, then the velocity vector will never change, which means the momentum will stay the exact same, which, if we were to look at it on some kind of graph, would just simply look like a straight line going this way. Now, this experiment calls for recording an observation of a ball traveling at the same speed horizontally, while also drawing up a computational model of the same thing, which will be done in GlowScript, I'll show that later, and then comparing the two via Excel spreadsheet or Google Sheets. Okay, now that we made a little bit of a segue into the tracker app, now I'm going to show you what the experimental part was, the observational part of the experiment was. So basically our initial conditions were a position vector of 0, 0, 0, a velocity vector of 0.62200, and the systems and surroundings, well, the system is the blue golf ball here, and then the surroundings are the table. Okay, so now that we're over to GlowScript, I'm just going to show you little things that I tweaked within the starter code to make it allocate towards my experiment directly. We have an fnet vector of 0, 0, 0. My ball position vector initially is 0, 0, 0, and the ball velocity is the same as the beginning velocity on my tracker app, which is 0.622. And finally, for the ball velocity, I applied the momentum principle, which is fnet divided by the mass multiplied by delta t, and then the ball position equals ball position plus ball velocity times delta t. So let's take a look at what that looks like. So basically, I plotted out the tracker app's exact measurements for time and then position them on the x-axis, and then I also plotted out the GlowScript's perfect ones as well. Okay, now that we're over to the iPad and we have the graph in a little bit more of a malleable setting, we can begin to discuss the similarities and differences between these two graphs. Now, the first obvious similarity, and one that's very good, is that the trend lines are both pointing in the exact same direction, which is inferring that as this block of time goes forward, the position of x also increases in amount as well. The observational line here is not perfectly linear. I have 4 reasons for this, and one of them is friction. Now, I devised friction as being more of a reason why this phenomenon is happening right here, because as the ball is rolling across the table, it could be encountering forces of friction that could end up slowing the ball down. This could be above the predicted line, which means the speed is actually going faster than predicted, could be up to human error. Okay, so just for a little what if the x-axes were switched? And what I mean by that specifically is, instead of the ball rolling this way, what if the axes were switched and instead of plus x, it was instead going in the negative x direction, rolling that way? Now, pretty simple. The position graph for the positive x, or the regular x, I should say, would look something like this if we were talking about p and then t. Now, if we were to switch the directions of how it would go, it would not look like this, no. It would rather look like this, where instead the position goes negative. Okay, so to end it off, I'm just going to ask a simple question. What does it mean? Can we dictate the number of pushes and pulls that this ball goes by as it rolls along this plane? No, there's zero way that we can actually say how many exact pushes and pulls are going off on this ball. Because it could be a mix of literally everything. Pushes to the left from human. That could be a possible push to the left. A push to the left from air conditioning. Even something as small as the air circulating the room could push it that way. And for pushing it to the right, it could be the exact same thing. It could be friction. One could be air resistance. It could be 1,000 things. But what is the most important about this observation is that no matter how many there are on the left side, no matter how many there are on the right side, if this is 100 newtons of force, this must also be 100 newtons of force in order for that to be 0 fnet. And it will travel with a constant speed across the table. Thank you very much. Have a great day.